Welcome to the Deep Dive. Today, we're tackling something vital for workplace safety, but honestly, often totally invisible: industrial ventilation systems.
That's right. It's all about occupational hygiene. We're going deep into how you control hazardous stuff in the air, basically controlling the air that you, the worker, breathe.
And our mission today.
Well, we're digging into the sources, looking at the two main ways it's done: dilution and local exhaust ventilation. And maybe the most surprising part, the really strict three-stage process required by law to make sure these systems are actually doing their job.
Okay, but first, where does ventilation even fit in the big picture of safety?
Good question. It sits under engineering controls in the hierarchy,
Mm.
meaning you always try to eliminate the hazard first or swap it for something safer. If you absolutely can't do that, then you engineer a solution, like ventilation.
So it's preferred over just giving someone a mask, the personal protective equipment, or PPE.
Much preferred. You want to fix the environment, control the risk before it gets to the person. PPE is really the last line of defense.
Got it. Okay, let's start with the simpler sounding one: dilution ventilation, DV.
Right. The basic idea is, well, simple. You don't try to capture the contaminant right where it's made. You just bring in enough fresh air to dilute it down to an acceptable level.
And you measure that with air changes per hour, ACH.
Exactly, ACH. How many times per hour does the entire volume of air in the room get replaced?
But you said it sounds simpler, implies limitations.
Huge limitations. Because it's so basic, DV really only works for a couple of things. Either keeping flammable vapors below their lower explosive limit, the LEL,
So they don't go boom.
precisely, or keeping toxic stuff below its occupational exposure limit, the OEL. But there are big ifs.
Okay, what are the ifs? Why can't I just use this for everything, like welding fumes?
Well, number one, the OEL has to be pretty high. Stuff can't be super toxic. Number two, it needs a low vapor pressure. It can't evaporate too quickly. But the real killer, the absolute deal breaker, is proximity. If the worker is right there where the contaminant is being generated, especially near their breathing zone, DV is useless.
Because they're breathing it in before it even gets diluted.
Exactly. The concentration might be fine 10 feet away, but right at the source, way too high. So the source needs to be, relatively far from the worker.
Makes sense. And even if you can use DV, fan placement isn't just sticking a fan anywhere.
Not at all. It's basic physics, really. Density.
Density of the contaminant vapor.
Yeah. Is it heavier or lighter than air? Most common solvents, their vapors are denser than air, heavier than one.
So they sink.
They sink. They layer near the floor. So for those, you need extraction fans low down on the walls.
And if it's lighter than air?
Then it rises fast. So you need fans high up, maybe roof fans. Get it wrong, and you're just swirling it around, not removing it effectively.
And even with the right placement you mentioned, dead areas. Sounds ominous.
It can be. These are just pockets in the room where the air isn't moving. It's stagnant. The air changes aren't happening there.
How do you even know they exist?
You can use smoke tracer tubes. Release a little smoke, and you can visually see where the air isn't flowing.
But the problem is, they move.
That's the kicker. They're unpredictable. Maybe you change where the makeup air comes in because it's winter, or someone props open a door. Suddenly, that dead spot full of contaminant shifts somewhere else.
Okay, so calculating the ACH is important then. Let's run through that quickly. Say a room, 5 meters by 5 meters by 3 meters high.
Okay, so 5 times 3, that's 75 cubic meters of volume in the room.
Right. And if the ventilation system pushes in, say, 1,000 cubic meters of fresh air every hour?
Simple division. 1,000 divided by 75 gives you 13.3. So that's 13.3 air changes per hour.
And you'd compare that to what the system was designed for.
Exactly. If the design said you need between 10 and 15 ACH for this process, then 13.3 tells you the fan's doing its job, volume-wise at least.
Okay, so if DV isn't good enough when workers are close to the source, which is often, we need something more focused.
And that brings us to local exhaust ventilation, LEV.
The targeted approach.
Precisely. LEV grabs the contaminated air right at the source, the point of generation, and ducts it away before it gets into the general room air.
And this can be tiny things like on a power tool or massive systems.
Absolutely. From a little vacuum nozzle on a sander right up to a huge walk-in spray booth for painting cars.
Yeah.
But structurally, they all share the same 5 essential parts.
Okay, what are they? Let's break it down.
First, you've got the hood. That's what collects the contaminant.
Right at the source.
Then, the ducts. The pipework that carries the dirty air away.
Makes sense.
Third, the air cleaner, the filter, basically. Got to clean the air before releasing it, usually.
Okay.
Fourth, the fan, the engine of the whole system, provides the airflow, the suction.
The power.
And finally, number 5, the discharge, the exit point, usually a stack where the cleaned air is released safely.
Let's talk hoods first. You said they collect the contaminant. Are there different types?
Oh, yes. And effectiveness varies hugely. The best, the gold standard, is an enclosing hood.
Like a laboratory fume cupboard? Or a glove box?
Exactly. The whole process happens inside the hood, maximum containment.
Okay, what's next down the list?
Then you have receiving hoods. These are a bit smarter. They don't necessarily need massive airflow themselves. They take advantage of the process's own air movement.
How so?
Think of a canopy hood over a boiling vat. The heat makes the steam and contaminants rise naturally right up into the hood. The hood just receives that flow.
Clever. And the last type?
The most common type, capturing hoods. Here, the process, the source of the contaminant is outside the hood.
So the hood has to actively pull the air in.
Right. It has to generate enough airflow velocity out in front of it to actually grab that cloud of dust or vapor and draw it into the duct. It's working against the room air.
This sounds like where things get tricky.
They do. This introduces 2 really critical ideas, the capture zone and capture velocity.
Okay, capture zone.
That's a specific space, the area right in front of the hood opening, where the airflow is actually strong enough to pull contaminants in effectively.
So if the worker moves the job just outside that zone?
Bingo. The LEV stops working properly for them. Even moving a few inches can make a huge difference. Positioning is vital.
And capture velocity.
That's the speed the air needs to be moving at the point the contaminant is released to overcome the energy of that contaminant cloud and pull it into the hood.
The energy of the cloud. So like dust flying off a grinder has more energy than vapor just evaporating.
Exactly right. Huge difference. For simple evaporation in still air, you might only need, say, 0.25 to 0.5 meters per second. Barely a breeze.
Okay.
But for high energy stuff, grinding, abrasive blasting, you might need 2.5 meters per second, maybe even over 10 meters per second capture velocity.
Wow, that's fast. That's like fighting a dust storm.
It really is. And those very fast-moving clouds, they're incredibly hard to control with just a simple capturing hood. Often you need to add partial enclosures, barriers, just to try and slow the cloud down first before the hood can grab it.
Okay, moving on from the hood. Ducts. Seems straightforward, just pipes, right? But you hinted they can cause problems.
Oh, they can be a major headache if designed badly. It's not just plumbing. Good ducting needs to be as straight as possible.
Minimize bends.
Yes, and the bends you do have must be gentle, long radius bends. And joins. They should come in at an acute angle, like a smooth Y-junction.
What's wrong with sharp bends or like a T-junction?
Massive turbulence. Huge pressure drops. It kills the airflow efficiency. And worse, especially with dusts.
Yeah.
You need to keep the air inside the duct moving fast enough. That's the transport velocity.
What?
To stop the particles from settling out. If the air slows down too much in the duct, the dust just drops out of the airstream, builds up inside the pipe.
Creating a blockage.
Exactly. It can choke the system, reduce airflow, and in extreme cases, the weight of accumulated dust could even cause the ductwork to collapse. You need maybe 20 meters per second transport velocity for heavy dusts, like from grinding.
For serious stuff. Okay, after the ducts, the air goes to the air cleaner.
The filter. Right. And what you use depends entirely on what you're catching. Is it solid particles, or is it gases and vapors?
Let's do solids first. Particulates.
Okay, for solids, you've got several options. Fabric filters, think of a giant industrial vacuum cleaner bag. Very common.
Okay.
Then there are cyclones. These spin the air really fast, flinging the heavier particles out to the walls by centrifugal force.
Neat.
Electrostatic precipitators use high voltage to charge the particles and collect them on plates. And wet scrubbers use water sprays to wash the dust out of the air.
You mentioned something surprising about cyclones earlier.
Ah, yes. Here's the thing with cyclones. Because they spin the air and particles so vigorously that friction can actually generate static electricity.
Really? Static?
Yes. And if the dust you're collecting is combustible, like wood dust, flour, some metal dusts, that static spark could be the ignition source for a dust explosion inside the cyclone.
Wow. So the safety device itself introduces a pretty major explosion hazard.
It absolutely can. It means you need really specialized grounding, bonding, maybe explosion venting. Managing that risk is critical. It shows how complex these systems get.
Definitely. Okay, what about cleaning gases or vapors? You can't filter those with a bag.
No. For gases and vapors, you usually need a different approach. Sometimes it's destruction, basically. You incinerate them, burn them off safely.
Okay.
Or you use tower scrubbers, where the contaminated air bubbles up through a column of water or a chemical solution that absorbs or reacts with the contaminant.
Washing the air?
Essentially, yes. Or there's recovery. This often uses filters filled with activated charcoal. The charcoal absorbs the vapor molecules onto its surface. Sometimes you can even recover that solvent for reuse.
Okay, last part. The discharge, getting the cleaned air back outside.
Seems simple, just blow it out. But again, physics matters. The discharge stack, the chimney, needs to be tall enough
Why tall?
to get the exhaust stream above the building's boundary layer.
Boundary layer. What's that?
Think of it like a sort of sticky, slow-moving layer or bubble of air that clings to the surfaces of the building, the walls, and the roof. It's caused by wind resistance.
Oh, okay.
If your discharge stack is too short, the exhaust just gets dumped into this slow-moving boundary layer air. And what happens? It can get sucked right back into the building's fresh air intakes.
Defeating the whole purpose, recontaminating the workplace.
Exactly. So the stack needs to be high enough to clear that layer, and the discharge velocity, the speed it comes out, needs to be high enough to disperse it effectively away from the building.
This is incredibly detailed. So you've designed it, installed it. How do you know it's actually working correctly day to day, year to year?
That's where the crucial final step comes in. The thorough examination and testing, often called text.
And this is a legal thing.
Oh, absolutely. New systems need formal commissioning tests to prove they meet the design specs. Existing systems, they need regular testing by law. In the UK, under COSHH, it's typically at least once every 14 months.
And not just anyone can do it.
Definitely not. It has to be done by a competent person, someone with the right training, knowledge, and experience to understand how the system should work and how to test it properly.
Okay, so this competent person comes in. What do they actually do? You mentioned 3 stages.
That's right. Stage 1 is pretty straightforward. A visual inspection.
Just looking around.
Basically, yes. But looking with a trained eye. Are there obvious signs of damage? Dents in the ductwork. Is dust settling around the hood opening, suggesting it's not capturing properly?
What else?
Broken seals. Is the fan making excessive noise or vibrating badly? Things like worn fan belts. You can often spot problems just by looking and listening carefully before you even get any instruments out.
Okay, makes sense. Stage 2. This sounds more technical.
It is. This is the quantitative assessment. Measurements. Hard numbers.
What key things are they measuring?
Usually 3 core things. First, face velocity. That's the airspeed right at the opening of the hood.
How do they measure that?
They use an anemometer. Could be a heated head type, or often you see the deflecting Bain anemometer looks like a little windmill. Robust bit of kit, needs no batteries.
And they don't just measure in one spot?
No. They imagine a grid across the hood opening and take readings in multiple spots within that grid. What you're looking for is consistency. If the velocity varies by more than, say, 20% across the face, the flow is uneven, and the capture won't be effective across the whole opening.
Okay, face velocity. What's the second measurement?
Transport velocity. That's the speed inside the ducts. We talked about this needing maybe 20 meters for heavy dust.
Right, to stop settlement? How's that measured? Inside a pipe?
For that, they use a different tool, a pitostatic tube. It's a thin tube inserted into the duct, connected to a manometer, which measures pressure differences to calculate the velocity.
Okay. And the third key measurement?
Static pressure. This measures the pressure perpendicular to the airflow, again, using a manometer connected to a port in the ductwork.
What does that tell you?
It's often used to check the condition of the filter. Filters create resistance, a pressure drop. If the static pressure reading across the filter is much higher than it should be.
It means the filter's clogged, blocked.
Exactly. The system is struggling. It's being starved of air because the filter is full.
Mm-hmm.
It's a key performance indicator.
Got it. Visual check, then hard measurements. What's stage 3?
Stage 3 goes back to being qualitative, but it's about visualization. Seeing the airflow.
Seeing invisible air. How?
2 main ways. For dust, especially fine, invisible respirable dust, they use a dust lamp.
What's that?
It's basically a very powerful lamp that projects a strong parallel beam of light. When that beam shines through the air near the process,
It lights up the dust particles?
precisely. It uses the Tyndall effect. The light scatters off the tiny particles you normally can't see, making the whole dust cloud visible.
So you can see exactly where it's coming from and if it's getting pulled into the hood or escaping into the breathing zone.
Exactly that. It's incredibly revealing for pinpointing problems with capture.
And the other visualization method?
Good old-fashioned smoke. Using smoke tubes, pellets, or generators to create artificial smoke.
And you just watch where the smoke goes.
Yep. You release it near the point of contaminant generation and watch. Does it get drawn smoothly into the hood? Does it define the capture zone clearly? Or does it just swirl around and drift away? It's a very direct way to assess if the hood is actually capturing effectively, especially for larger systems.
So visual, quantitative, then visualization. That's thorough. What happens after the test?
Well, the process isn't over. The competent person has to write up a detailed report what they tested, the results, whether it passed or failed against its design performance. And if it fails,
Fails.
if the system isn't performing as it should, isn't providing the intended protection, it gets a fail. And the examiner is often required to put a clear, bright red fail label right on the hood itself.
A warning sign.
A very visible warning sign that this control measure isn't working properly. And the employer has a legal duty to keep that text report record for typically 5 years.
Documentation is critical then. Proof it was checked, proof it failed, basis for getting it fixed. Wow, we've gone from just blowing air around with dilution ventilation to this incredibly complex 5-part LEV system and then this rigorous 3-stage testing.
It really highlights how much engineering and ongoing effort goes into something as seemingly simple as providing clean air in a workplace. It's a constant process of design, maintenance, and verification.
Absolutely. It's a hidden science keeping people safe. Okay, so we often focus on the hazardous substance itself, the gas, the dust. But here's something to think about, our final provocative thought for you. The LEV system is there to collect that hazardous stuff, right? But think about what's inside that system. Besides the noise it makes, how might the accumulated material inside the ducts, the filter, the collector, especially if it's flammable dust like wood or flour, or even explosive metal dusts, how might that collected hazard itself present a massive, potentially catastrophic risk that needs its own specialized management and cleaning regime? The safety system could contain its own disaster waiting to happen.